Hi, welcome to REGENTS Chemistry Review. I'm Mr. B. During this lesson, I will relate potential energy diagrams to both endo and exothermic reactions. Endothermic reactions absorb heat energy. In the equation for an endothermic reaction, the heat energy is always written on the reactant side. And exothermic reactions release heat energy. In the equation for an exothermic reaction, the heat energy is always written on the product side. Let's relate endo and exothermic reactions to potential energy diagrams. The potential energy diagram for an exothermic reaction will go from high to low potential energy. The potential energy diagram for an endothermic reaction will go from low to high potential energy. A potential energy diagram has different regions representing different amounts of potential energy. Potential energy is stored energy. A potential energy diagram will provide a relative measure of the amount of energy stored in the reactants and the products in a chemical reaction, and the change in energy that occurs as the reaction proceeds in the forward or reverse direction. If you're asked to identify an endo or exothermic reaction, look on reference table I. And if you're asked to relate one of these reactions to a specific potential energy diagram, remember that reactions with negative delta H values will fit the exothermic potential energy diagram, and reactions that have a positive delta H value will fit the endothermic potential energy diagram. Now I will explain how to label potential energy diagrams, beginning with the potential energy diagram of an exothermic reaction. This is an image of a potential energy diagram representing an exothermic chemical reaction. Each number represents either the potential energy or a change in potential energy during a reaction. Let's identify and label the regions on this particular diagram one by one. Number one, the PER, the potential energy of the reactants. This is the total amount of potential energy contained in the reacting particles. Region number two, the energy of the activated complex, or the EAC. This represents the total amount of potential energy contained in the entire reaction, including the activation energies. Number three, the activation energy. This is the total amount of energy required to initiate a reaction. For example, striking a match to light a burner is an example of activation energy. Number four, the delta H. The delta H is the heat of reaction. It represents the difference in the potential energy of the reactants and the potential energy of the products. Delta H represents the amount of heat energy lost during an exothermic reaction. For an exothermic reaction, the delta H value, by the way, will always be negative. And finally, the potential energy of the products. This is the total amount of potential energy contained in the products formed during the chemical reaction. Now we'll identify the regions found on an endothermic potential energy diagram. Region number one, the potential energy of the reactants, which of course represents the total amount of energy contained in the reacting particles. Region number two is the activation energy. On an endothermic potential energy diagram, the activation energy will include delta H, and delta H, which represents the potential energy of the products minus the potential energy of the reactants, or pepper for short. On an endothermic graph, the delta H will have a positive value. Region number four, the energy of the activated complex. An activated complex is the highest point on the graph. So the energy of the activated complex represents the total amount of energy in the reaction. And region number five is the potential energy of the products, or PEP, the total amount of energy contained in the products of the reaction. Now for the effects of a catalyst on a chemical reaction. A potential energy diagram is particularly useful in explaining the effect of a catalyst on a chemical reaction. Consider the decomposition of potassium chlorate, KClO3. A catalyst will lower the activation energy in the reaction. This will provide an alternate pathway, thus causing the reaction to occur at a faster rate. Now let's practice for your upcoming Regents examination. Consider the following questions. Base your answer on the potential energy diagram of a chemical reaction. Which arrow represents the activation energy for the forward reaction? Well, the correct answer to this question is number 1, A, where the activation energy for this type of reaction, which is endothermic, will include delta H. The potential energy diagram shows the reaction X plus Y gives Z, and it shows an equilibrium condition. When a catalyst is added to the reaction, it will change the value of which of the following. Okay, so a catalyst lowers the activation energy. So the regions affected will be, well, clearly region 2 and region 3. Regions 1 and 4 will be unaffected, so the answer is number 2, regions 2 and 3. In which potential energy diagram does the arrows represent the activation energy for the forward reaction? Once again, the activation energy questions are coming up over and over again. Keep that in mind. At any rate, the activation energy for the forward reaction is represented by choice 2, where the arrow shows the activation energy of an exothermic reaction. Which interval in this diagram represents the difference between the potential energy of the products and the potential energy of the reactants? Okay, this is going to be delta H. For short, remember delta H as pepper, the potential energy of the products minus the potential energy of the reactants. And the correct answer to this question is line 4. And finally, the chemical reaction between methane and oxygen is represented by the potential energy diagram and balanced equations below. Explain in terms of the collision theory why a lower concentration of oxygen gas decreases the rate of the chemical reaction. Well, according to the collision theory, increasing concentration will increase the number of effective collisions. So decreasing the concentration of one of the reactants will decrease the number of effective collisions. So decreasing the concentration of oxygen gas will decrease the number of effective collisions. Okay, this concludes my review of potential energy diagrams and endo and exothermic reactions. Hopefully this lesson has been helpful. And remember, should you require more assistance, feel free to visit my Facebook page at facebook.com/WPHS Chemistry. Thanks for watching. And remember, good luck on your upcoming examination. I know you'll do well. Take care.